Hello. Okay. Good evening, everyone. Welcome back to NPTEL live session for the course Advanced Transition Metal Organometallic Chemistry. So, at the last, we have covered all the different kind of ligands. For example, C5H5, C6H6, or you can call it as arene. This is CP or CP star. Then we have taken into consideration C7H7, and also we have talked about C8H8. So these main ligands, and earlier lectures were regarding the allylic ligands. So these we have covered so far. And now the last lectures are regarding the coupling reactions. So what we have ended up with, the CC, just an introduction about the CC coupling reactions that we have started with. So we'll just quickly look around it. So CC coupling reactions are one of the important reactions, not just in the inorganic chemistry. When we look around the organic reactions, organic synthesis, these coupling reactions play a very important role. So among them, some known reactions are Heck reaction, Suzuki coupling, Stille coupling, Sonogashira, hydrocyanation reaction. So we will be taking a one at one time, explaining all the details, the mechanism, and different examples. So for example, CC coupling reactions, as I told that this is an essential reaction in organic synthesis and also a hot research topic. Palladium is most often used in these CC coupling by among palladium, rhodium, iridium, platinum. So these are what we call noble metals, and also they have a nature which is less abundant. They don't exist in much abundance, but among all of them, palladium is known to have less toxicity compared to all of those other three, rhodium, iridium, and platinum. And also it can tolerate different kind of functional groups. For example, it is not going to react with those functional groups, so it has a tolerance regarding those functional groups. And when we talk about, if I'm using a certain amount and it is getting consumed and giving a product, that is what we call an atom economical. So when it has to be, that atom economy has to be there, and also compared to these three, it is economical. So the comparison has been made very clear. Now, this was what we have taken last time, a simple comparison between the catalytic mechanism and the stoichiometric way of reaction. How the two things give the product, but what kind of other things are involved in how the catalyst term comes into picture. So earlier what we saw, that we are taking the substrate Rx, where R could be anything, that could be a aryl moiety or an vinyl moiety or anything like that. And we are taking a metal which is in plus, which is in zero oxidation state. Firstly, it will go and have an oxidative addition. These we will see in detail, where both R and X are coordinated to the palladium now. And once you have a nucleophile, now you want to have a nucleophile interaction with your R, or you want a product which R and you want to form. So how you will form? Now here the transmetallation or the metallation will happen where nucleophile from this particular metal will go and bind with the palladium, and this X will be taken up by this metal. Ultimately, due to the reductive elimination, we will be ending up having our nucleophile as a product, and palladium zero is regenerated. That's why we call it as a catalyst. It is reducing the activation barrier, and also it is regenerating in the catalytic mechanism, continues to give the product for a longer time until unless its lifetime is gone. But when we talk about the stoichiometric fashion, here same substrate we have taken Rx and we are using a Mg, which is magnesium in zero state, and this is called a Grignard reagent. Now it has gone to 0 to +2. Now we want to have this kind of moiety attached with the R, and therefore we reacted it, and ultimately we end up having a product which is another Y could be anything. It could be another X also, halogen group also. So it could leave as MgCl2 or MgBr2. So here, what we saw, we started with Mg0 and it ends up having a magnesium salt. So it is not going back to its +2 to 0. So it is not at all a catalytic. That's why it is called a stoichiometric ratio. So you started with 1 mole, you are ending up having a 1 mole of product, and that is it. You cannot expect to have an increase in the product. So that is a basic comparison between the catalytic fashion of the reaction of CC coupling and stoichiometric fashion. So moving ahead, here we are basically talking about the palladium and in what state. So some reaction needs palladium in +2 species. For example, olefin oxidation, if you say dehydrogenative aryl coupling, oxidative carbonylation, which will be converted to palladium zero. But some reaction needs palladium zero, that is Wacker oxidation, which will be converted to the palladium 2 positive, for example, the down one. So here what happens, we are talking about the Wacker oxidation, where copper is playing as a catalyst, and also palladium 2 is the active species. So it is required to gain the oxidation state of copper back. For example, we have taken the 2 proton and half oxygen, and once it is being treated in presence of copper plus, so copper plus has a tendency to lose 1 electron to give copper 2 positive, and that 1 electron is being gained by this particular moiety to give a water molecule. So this is the reduction step, and this is getting oxidation. And once we need this reduced species back, now it has been oxidized. Now it has to be reduced back to copper +1 to redo that whole mechanism. That's why we added palladium 0, which has a tendency to get oxidized to palladium 2 positive. That means it will lose 2 electrons and it will be taken up by 2 copper positive. So that is where it says that for coupling reactions or different kind of reaction, in coupling reactions, generally we talk about the palladium 2 positive, which will go to the palladium 0, and then it will convert to 2 positive again. Some reactions, it starts with the palladium 0, and then it goes to the palladium 2, and then comes back to palladium 0 again. So here our actually lectures start, which has been taken in week 8. So they have been started with the lecture 36. Here we will be talking firstly about the alkylic alkylation. So we will just see what is alkylic alkylation. It is also kind of CC coupling reaction. So CC coupling in alpha position is well studied. We know that alpha position, how it is happening, whereas the coupling at allylic position is overlooked. For example, here, so we have a carbonyl here, and near to this, adjacent to this carbonyl, that is called the alpha position. So that is called alpha carbonyl alkylation. And similarly, if I'm taking an allylic group, here this is with respect to this allyl group, this is an alpha position, and here we are having an R. R could be anything, and this is called allylic alkylation. Okay, so with respect to that, what we mean to say when we are talking about the carbonyl group and the adjacent to it, it is known as alpha, or if one more moiety would be there, then it would be called as beta. So allyl carbonyl alkylation we have seen. But when we are taking an alkyl position over here, so having an substitution on this particular position, we term it as alkylic alkylation. So the mechanism goes through this particular way. Here also we will be using a catalyst which is comprising of palladium. So palladium L4, it is having 4 L ligands. L stands for the ligand over here, And since here it has been defined that L is nothing but your PPH3. So when it is PPH3, that means it is in zero state. It is not having, PPH3 is not having any charge, that's a neutral ligand. So it would be in zero state, and on loss of two ligands, that two PPH3 molecules have been lost, it is still in zero state. Now it is having the electrons. So when it is having the electrons, it can give electrons to the other species to get bonded. So oxidative addition happens. This step, the first step, that is oxidative addition. That means this allylic moiety and this X, they bind with the palladium because it is having the palladium is in zero state, and it can easily give the two electrons, one to alkyl allylic portion and one to halide. Similarly, here if you'll see, these two are neutral, but here it is having a sigma bond with this and an X is binded with this. So one charge would be coming from here, -1 here, so it becomes +2. Now its oxidation state has been changed from 0 to +2. That is why it is called as oxidative. And addition has happened because on the same side of the palladium, we are having X also, and we are having the allylic moiety also. But if we'll see and remember the first lecture of the week 1, we have talked about different interactions of the allylic moiety. So here it is bound as in sigma, but sigma to pi rearrangement can happen at any point of time because that is fissile, and it will now contribute 3 electrons. So all the 3 carbons are now interacting with the palladium, having this resonancing. And therefore, when 3 electrons comes into picture, X has to be lost because 1 electron was coming from there. Still the 1 charge is extra. That's why we have given a positive over there, which is balanced by the X negative. Now, when we have this pi allylic formation, now easily any nucleophile which we want to get attacked, which we want to get added on the allylic position of this allylic moiety, the nucleophile comes over here and it attacks, if I'll show here, it attacks here, and therefore it goes off by this product, and we are ended up having the PDL2. So it is again coming back to its original form. For example, even if we are just trying to analyze it, if nucleophile comes into picture and connected with the palladium, and we have this allylic position, there would be a reductive elimination, and then palladium +2 will again go back to its zero state. So this is the whole mechanism that is involved in allylic alkylation, where palladium 0 is going to palladium +2, the moieties are getting added, and then they undergo sigma to pi rearrangement, then reductive elimination, and we are ending up having a nucleophile addition on the allylic position. So the also one more important thing regarding the regioselectivity, from where the nucleophile is going to attack. So the region that we have to be very specific. So it says that nucleophile prefers to attack from the less hindered side of the eta3 allyl ligand. Nevertheless, some electronic effect of the catalyst also play an important role. The tendency of the leaving group is also considered. For example, if we have these kind of leaving groups, Cl would be the one which will leave at the fastest rate compared to the OH which comes at the end. So whenever we have two positions and nucleophile has to attack, it will prefer to attack from that position where it will be less hindered. That is very straightforward example. For example, here now we are talking about the asymmetric allylic alkylation. That means it will give you chiral center. So this moiety is having a chirality with OAC, and here is the nucleophile over there. And now we have this palladium. Don't get confused and by this particular moiety. This is just a ligand base, and there we are having a palladium over here. And again, it is in zero state. And ultimately, we are ending up having this kind of product. So as you can see over here, O acetate becomes a leaving group, and it can easily come and attack on this particular position, which is the allylic position of this particular moiety. And once you give this undergoes further reactions, it will end up having this particular product, which is having 90% yield and 99% enantiomeric access. So diastereomeric ratio, if we are changing substrate from to methyl, it would be giving a 8.7 to 1 ratio. And if we are having an isopropyl, that would be more than 19. So 19:1 ratio we are getting. So this will tell you about enantiomeric axis, like which form will exist in which ratio, and depending on the different substance, we can have different enantiomeric ratio. So now the 37th lecture was about, this was the earlier one was about the alkylic alkylation, where we saw that how palladium goes from its zero state to +2, involving the oxidative addition, then sigma to pi rearrangement, then we are having a neutrophilic attack, and ultimately it would give you the required product. Now we are moving to another coupling reaction, which is the Heck reaction. It also involves the palladium catalyst, but the conditions are different. So what is Heck reaction basically? Since all the coupling reactions more or less involve the palladium catalyst, so you need to remember the kind of conditions that has been employed to have that particular CC coupling. We cannot intermix all these conditions. So for example, in Heck reaction, there is a replacement of vinylic proton by vinyl, benzyl or aryl group. So this is particularly for the vinylic proton in presence of a base. Okay, so these are the conditions. We are having a vinylic bromide and also vinylic, where we have a carbonyl moiety, and in presence of base under 100 degrees Celsius, and these are the catalytic conditions. Here 1% palladium acetate, that means salt, and the ligand are being added in situ, and they are making the complex in situ which is involved in the reaction. And ultimately we are having this particular Br will go out, and then it will attack on this particular position, and we will be ending up having CC coupling over here. This bond is a new bond formed between this one and this two. So this is a Heck reaction. We will look into the mechanism quickly. So as I said that we started with the palladium O acetate, which is in +2 state, and but we are putting the L equals to PPH3, that is your ligand. So ultimately it would be having, we are adding the base also, take up your acetate very easily, and ultimately we will be ending up having palladium L2. So if it is started with +2, and ultimately if you want to have an oxidative oxidation, it will not go to its +4. So it has to go to its firstly 0 and then goes to +2. So it is in 0 state. Again, when we are having an R-X, this could be vinylic bromide or anything, bromide or any halide. So the vinylic moiety is there, and palladium goes to +2. So this X and R, they are in trans form. Now, when we have, generally it will end up having an transposition moiety. So we will have the mechanism in that direction only. So another moiety whose group we want to attach with this vinylic group R dash. Now, since this is an alkene and we have a metal alkyl bond, it can easily undergo the coordinative insertion. What I mean to say, when metal and alkyl, metal and R is here, and we have a alkyl group, alkenyl group over here, it can easily go and bind and attack on this particular position, where R could go and attach on your different positions. For example, this R is coming, this position is 1 and this is 2, and 1 is attacking on the palladium, and subsequently this will go and attack on your alkene bond, and hence there is a bond formed between this carbon and this R dash. And now you can see that this is alpha and this is beta, because it is directly attached over here, and this beta hydrogen becomes very labile, and after the beta hydride elimination, we will be having a trans alkene formation, where earlier it was R-X. We wanted to have a R over there, and this, therefore, it has formed the product and given back our X and H. Now we are giving the base, and base will take up your H also, forming a protonated ammonium is there, and which will be balanced by the X. And ultimately, we will be ending up having PdL2, that means palladium L2, coming back from its +2 to 0 state. So the catalyst, the catalytic cycle continues to grow, and we will be having a product in large quantity. So this is how the Heck reaction mechanism occurs. So we will just take up the general points over here, what we have seen. So firstly, there would be, since palladium O acetate is there, and we are giving L equals to PPH3 in presence of base, it will form palladium L2, which is in 0 state. followed by it will be having an oxidative addition of that vinylic halide, and followed by that we will be having an coordinative insertion where of another alkene, or something like that, or vinylic or any other group. Then ultimately it would be having a beta hydride elimination, followed by reductive elimination, and ultimately we'll be having our product. So this is the whole mechanism for the Heck reaction. So these are some points which I just explained to you. So oxidative addition of R-X palladium 0 giving trans this moiety. To avoid the rapid beta elimination, R-X. So we need to keep one thing in mind. For example, if I am at the very first step, if I'm having this L, X, and R could be anything. Say, for example, so for example, if it is having this beta hydrogen over there, so you can easily go and attach with your palladium and it will give you alkene at the very first step. So that you need to avoid. So we need to take up the substrates only those who are not having any beta, which should not give you any beta elimination thing. That means we cannot have this kind of allylic group where it is having this beta hydrogen over there. So the possible groups could be vinyl, benzyl, or aryl group, which are devoid of any hydrogen, which could undergo for the beta hydride elimination. The second step is to insertion of the olefin to the palladium C bond, as I told you. And the third step is the beta elimination to give you the substitutive product. And the regeneration of catalyst when the base has been added and it will give you the palladium to +2 to 0 state back. So besides this chemical investigation, there is also electrochemical investigation. That means how the electrons and they are playing role, and which suggested that participation of anionic palladium species in the catalytic cycle. For example, if we have two ligands which are PPH3 and palladium acetate we have taken, so two electrons, and with the loss of one acetate, they would be having one charge, so this becomes an anionic complex. And when this becomes, they would be having an involvement of the substrate. This is your substrate, which is going to bind with your palladium. And ultimately, this is there. This emphasizes the influence of anions in the rate of oxidative addition. So from this particular thing, we can analyze the rate of oxidative reaction, how fast, how slow it is going, and what would be the possible rate. Now, oxidative addition is one such thing that we have discussed very oftenly, but the insertion step is also very important, which is followed by the oxidative addition. So how this steps occur? This insertion is preceded by the coordination of alkene to palladium. So first step was to have this palladium L2 with R-X. So palladium L, R- and X. And followed by when we are having another R, or we are taking up any alkene over there, for example. So firstly, it has to undergo with this pi interaction happens. So this alkene actually coordinates with the palladium. And now, as you can see here, we know that this bond has to be formed with this position, and this has to go and form bond with this particular thing. And R and palladium bond has to be broken. That's why it has been shown in this dotted sheet that R and this position of alkene is making a bond. This breaking bond, I will show it with red. So this is breaking. This is making, and this is also making. So these are two bonds are making and one is breaking. That's why we are ending up having the sky blue. I will show you like this. So this new bond is with this one, and This is also. So this one also has been made. And what was the earlier bond? This highlighted in red, that has been broken, and we end up having this kind of coordination where then it will undergo to give you the required product. So this undergoes with a concerted mechanism. The cyclic ring has been. So I hope this is well understood. Now following Heck reaction, annihilation of the styrene we have to take into consideration. So here is our palladium, which is already in +2 state. So it has already come to that after the oxidation step. This is the ligand. And pH and pH, since this is bidentate, so we are not using L2. And here are the allylic, that group that we want to have. This is pH, annihilation of the styrene. So now there could be two possibilities. Either it could give you a cis product or it could give you a trans product. As always, the trans product would be the most stable one. So it would come as the major product. And also it depends upon the solvent, what we are taking, and the halide that we have taken. So if we are taking a triflate with the solvent DMF is to water, that means a polar solvent 9:1 ratio. Ratio of trans would be more, but there would be a comparable formation of cis and trans. Whereas if we go to triflate with THF, which is comparatively less polar than DMF and H2O, so it will give you 92 as trans, 92% as a trans product. It's major and exclusive product compared to the cis one, which has only been formed in 8%. So the role of X negative and the role of solvent chosen will definitely define the percentage of your cis and trans product. So this is really, really important. Now, the another one is annihilation of the styrene. The model stoichiometric study of the annihilation of styrene suggested that regioselectivity depends upon the degree of cationic character of the arrayed palladium intermediate. That means if we have this particular thing, so regioselective we have to see. For example, if you have a 2-way where beta elimination can form, for example, this alkene has already come into that alkene has already coordinating with the palladium and it is having this hydrogen. So this is a group that we were talking about. So we should not be having any kind of so this could be a one thing that we should not have any kind of group which is having the beta hydrogen elimination possibility. That will come as an alkene at the very first step and it will stop further, or it is the another step where we are having the alkene coordination and there is two possibility of beta hydride elimination. So if it goes from this particular hydrogen where, because this is alpha and this is beta and this is beta dash, you will say. So if it is beta elimination, then the bond would be formed between near to the R1 and R2. And if beta dash elimination happens, then their bond would be here. And the bond would be like alkene would be formed near to the R3 and R4. So competing beta elimination of the inserted product also governs the kind of regioselectivity where we are going to have that alkene. So this also we have to keep in mind very carefully. Now moving towards the lecture 38, another kind of CC coupling reaction. We are done with the allylic alkylation. We are done with Heck reaction. Now we are talking about the Suzuki reaction. So Suzuki reaction is also frequently encountered CC coupling reaction. Palladium is used in most of the cases, as I have already told, because of its tolerance, functional group tolerance, and other factors of being economical compared to iridium, rhodium, and platinum. And here, the major feature for the Suzuki reaction, it uses a boronic acid as the coupling partner with alkenyl, alkanyl, or aryl halide. So earlier in Heck reaction, we have seen that it is basically working with the vinylic halides or whatever the other substituents, and it needs a base over there. and it requires those substrates only, the nucleophiles, which would be devoid of any beta hydride. So here the main feature is to have a boronic acid, which will act as a coupling partner with your other substrate. So this is a boronic acid where RBO OH, the valency is completed, and we have R dash X. So this R is going to couple with the RX, and we will be having a byproduct of BX OH wise. So here again, we are having a palladium in zero in presence of base. It will go to some further reaction steps. So this is the mechanism. So the mechanism says that R could be anything: allyl, benzyl, aryl, alkenyl, alkanyl. So we are starting with this palladium salt as we have seen earlier. Palladium L4 we can start with, or palladium salt we can start with, where it is combining to with the neutral ligands. And in presence of base, it will easily give you the palladium in zero state having two coordination. Now it is having the coordination number also and the electrons also to give to the Rx, R as I have defined. These are the different R could be possible, and these are the X, where the rate of reaction would be maximum if we have iodide, followed by triflate, followed by bromide, and followed by X, a leaving group ability. So here R and X have been coordinated with the palladium, and then palladium has gone to its 0 to plus state. This is called oxidative addition. This is your first step. Now, when we have another moiety, the substrate, the counter that we were looking around, the coupling partner, where boronic acid itself would be having that R moiety, which is going to attach with your R. So here, when we are taking this boronic acid, in presence of base, because it is a Lewis one, it will definitely get attached with a base having the negative charge. And once this anionic thing comes into picture, it will easily take up your X, which is your leaving group. Because this is also having a negative charge, so this particular R dash could be replaced by this X very easily. So it will take up the X, and R dash will come into this picture, and we will be having this anionic thing. And the bases that has been employed, that could be NaOH, NaOH, sodium carbonate, phosphate, tetrabutyl ammonium fluoride, anything. So now we have R and R dash. So for the coupling, there would be a trans-cis isomerization. This is the third step, which is very important. Earlier, these two moieties are trans to each other. For having the coupling to happen, we need to have it in cis form. So easily they will be having in cis form. So the coupling can be very facile. We will be having our product, R, and the CC coupling has happened. And ultimately, we'll end up with this palladium L2, which is again in zero state. So this is how the Suzuki reaction is occurring. It is more or less same as that of Heck reaction. The basic steps remain same, that how it is going from 0 plus 2 to 0, and then oxidative addition takes place. In case of Heck, it was involving that alkene into picture, so insertion has to be taken. But here we are adding the substrate as the boronic acid, so it will take up your leaving group halide, and then trans to cis isomerization will occur. In case of Heck reaction, it was beta hydride, because that substrate was particularly for the vinylic thing, so it has to undergo that alkene formation only. So that Heck has been designed for that matter. Here the R dash, it is not involving any beta hydride elimination. It is anyway involving trans-cis isomerization, which will lead you to have your desired product. So then, what are the benefits that we have from the Suzuki reaction? So boronic acid, why they have used boronic acid. Boronic acids are quite stable. Okay. So as we were saying that boronic acid are very stable. So they are stable, they are easy to handle, they are water and thermostable also. So the quaternization of boron is necessary by using the base to form a boronate anion, and they are actually acting as a carbon ion transfer agent. So when we were having this RbOH2, so boron is still a Lewis acid. So to transfer this as an R negative, we need to make it as a RbOH whole twice as a negative. So the charge would be more on the R and that it can easily attack on the metal. So that is why boronic acids have been become the coupling partners, and they have additional advantages of being very stable. They are easy to handle and they are water and thermostable. And why the carbon ion has to be formed, why this boronate ions have to be formed. So the transfer reaction should be very fissile. So these are the few points that you need to remember. That cycle starts with the oxidative addition. As I told you that palladium 0, L2 will go to palladium +2 because L, R and X would be having when we are involving the Rn. Then the transmetallation takes place in Heck reaction, alkene insertion. In Heck reaction, we have said the alkene insertion takes place, but here the transmetallation takes place. Why we are calling it transmetallation? For example, palladium was having an X. I'm not writing all other substituents over here. It is for the understanding purpose. And R is attached with your boronate anion. So this was OH2 and base. This is negative. So R is attached to the boron and X is attached to the palladium. And when they interchange with each other, palladium will take up the R and boron will take up the X. So the transmetallation, that's why we call it as the exchange of the moieties, and that is called as transmetallation. Then followed by the cis-trans-cis rearrangements, because okay, we'll not term it as isomerization. We should better say it as rearrangement. Okay, so yeah, so followed by the trans-cis rearrangements and then followed by the reductive elimination, which will give you the product. For example, here it is already in +2. We are having R here, R dash here, L here, L here. Ultimately, when R and R dash couple together to give out the product, we will be ending up having L and L, which is in zero state. So this is called the reductive elimination. Oxidative addition and reductive elimination, they are the complementary steps of each other. Now, again, enough advantages of the Suzuki reaction. They will involve a wide variety of substrate tolerance. For example, OH, NH moiety, carbon monoxide, nitro group, cyanide group, etc. So that means functional group tolerance is still there. It is maintained. We can call it as a substrate tolerance. So it is not interacting with those. Low toxicity of the reagents that we are using, the boronic acid and the palladium, compared to other things that is having a low toxicity. High selectivity of the cross-coupling product. So whatever the things we are getting, they are selectively giving you a one exclusive product, or it is formed as a major product. And also it is economical when compared to the rhodium and iridium. These are the basic points that we have read or understood in the very start of the lecture. Now, the preparation of that organoboron reagent, that is also very important. So, by metathesis reaction, metathesis is nothing but the breaking of the bonds and exchange of the bonds. For example, we have RLi, which is negative, and this is positive. And we are having B boron with the isopropoxide group. So, when it combines, it will give you this lithium, and this becomes a negative charge. On subsequent acidic hydrolysis, you can even write it as H positive / water. So we will be ending up having this organoboron because the R group is now attached with boron, which was earlier attached with lithium. Lithium goes off as a positive metal, and we get the isopropanol as a side product. So this particular thing that avoids multiple alkylation of the boron. So this will not, the triisopropyl thing will avoid the multiple alkylation. So we will be having only one time alkylation because the groups are very heavy and they will not let to have another R group with the loss of isopropanol group. So as you can see, the bond was between R and Li, and it has now gone to the RB. That is why it is called as metathesis, which is the exchange of the bonds. As I have told you in earlier lectures, when we are having R1 and R2 in this region and R3 and R4 here, and here if we suppose having H, H and HH, so olefin metathesis will happen like this way. It will be having R1, R2 here, R3, R4 here. The groups have been changed, and HH we will be having ethene group. So this is where these groups they combine together, and the other two sides would be combining together. Now the advantages of Suzuki reaction to functional group tolerance. For example, we are having this bromide and acyl group is there, nitrogen is there. So it is not going to affect anything. This is the R which has been attached. So this is organoboron reagent. So it can be applicable to anything. Only we need a R bromide or halide and that organoborane reagent in presence of our catalyst system and base. So you can see, I will just go over here. So this bond will be forming here. So it will give you Br, B, OH, twice having the base also, as we have seen. And the new bond is formed between these two. This was R, this was R dash. So R and R dash coupling has been occurred, and you can see the percentage is bit high, 70% of the product that we have got. So in lecture 39, the CC coupling reaction, again, we are talking about the Suzuki one. So advantages of Suzuki reaction for the regio and stereo control. So here this reaction is particularly for the formation of retinol, which is nothing but the vitamin A. So this is very important how it is getting synthesized. So we have taken, if you consider this as R and I, this is a halide group, which is a leaving group, and R we are having this full moiety. And here this moiety is R dash, which is attached with the BOH2. So if you just know that how the Suzuki reaction works, you can form the product without even looking at the mechanism, because the catalyst is there, the base is there, and the required solvent is there. So as we were seeing, 1, 2, 3, 4, 5. So 1, 2, 3, 4, and 5. And here, if you will see from this particular side, 1, 2, 3, 4, 5. So this one, these are the 5 and these are the 5, and there is a bond between these two R and R dash moieties, and ultimately it is giving you the retinol, which is coming as a 80%. So the trans-retinol aldehyde counterpart functions as a chromophore. So this is an advantage. If we have a trans thing, then it will act as a chromophore in bacteria. So this is the application of the Suzuki reaction. We have already seen that how it is working. It is different from Heck reaction in a sense that it is involving organoboron kind of compounds compared to the Heck, which is involving the vinylic moieties. Also in Suzuki reaction, the catalyst, and in Heck reaction, the catalyst more or less the same. But the main feature is the borane part, where organoborane compounds has been included in the Suzuki reaction, which is actually acting as a coupling partners. And this is having an advantage over the giving a high selective product and various other applications. For example, it is having a high tolerance for the other functional groups. So it can control and it will tolerate the presence of other functional groups, and it will not undergo any kind of further reaction. So the multiple coupling also takes place if we have that center. So as you can see, this is also an organoborane moiety, where these joints become the position where that coupling would happen. And here also you can see the bromides are there, and it will ultimately end up having the bonds between these two. For example, if we are having this R group over here, and then this will attach with the biphenyl group, and it will continue to do so. which will give you n equals to 100. So these many moieties can come, and this polyphenylene is used in LEDs and conductors. So this is also an application-based synthesis. So the polyphenylenes have been formed and multiple coupling is happening because they are having dead centers. Now, the asymmetric Suzuki reaction, again, we just have to look at this R moiety, which is connected to the organoborane. Here, this is the leaving group. And this whole, we can call it as R dash. So we are expected to have R and R dash over here. And because of these rings, it will tend to have asymmetry over there. In presence of this ferrocene kind of moiety, the co-catalyst has been used for this palladium Cl2. So as you can see, this is above plane, and here also some dark shade is coming for the above and below plane. So it will give you an anisomeric access. So this can be used as a chiral catalyst. Now, another thing is aryl chlorides in Suzuki reaction. So the classical method favors bromides, iodides, or triples. It's very difficult to have that chloride thing because it is the least among those which is having the leaving group property, that property we were talking about. Iodides would be maximum, then followed by triplet, and then bromide, and at last would be chloride. So if we use a suitable ligand, for example, bulky ligands and the electron-rich phosphenes, then chlorides could also be coupled. For example, this whole group, which is attached with BOH moiety, this is your R. And this whole thing, we can call it as, we name it as R double dash. This is R triple dash. And ultimately, we will be having a coupling between this R and R double dash and R triple dash with the loss of this Cl, BOH whole twice. So this is happening when we are taking this kind of bulky and electron-rich phosphenes. So earlier we were having generally PTH3 only, but because of the tertiary butyl group, on the phosphorus, it has increased the steric hindrance on that ligand. And when the ligands are being attached with the palladium, it will definitely increase the steric hindrance. And that will make the reductive elimination even more facile. And because of the electron density, it will make the attack more feasible. So these are the basic points that we have talked about the Suzuki reactions. This is very, very important. Now, moving towards the last lecture of the week 8, which is the Stiller reaction, that is one of another CC coupling reactions. This is also palladium catalyzed CC coupling reactions. So this basically uses the tin organelles. For example, earlier in Heck reaction, we saw the vinylic moieties, vinylic substrates. In Suzuki reaction, we saw the organoborane substrates, and in Stiller reaction, it is basically using the tin organelles, where this is playing an important role. So this R1, X, and R2, S and R3 to the Na3. So R1 and R2 couple together to give you this particular tin halide moiety in presence of the same palladium catalyst that we have been using in Heck reactions, Suzuki reactions, but the different conditions could be there. So again, some important points. The electrophile Rx should not contain any beta elimination pathway. This is same as that of the Heck reaction. That substrate that we are using, that electrophile that we are using, that should not contain any beta elimination thing. That hydride should not be there to have the beta hydrogenation possibility. Also, they are also having function group tolerance. These many function groups they can tolerate, they will not undergo any kind of further reactions. So the reactivity of tin organelles. So if we have R like this alkynyl, that means triple bond, double bond, aryl group or allyl group, benzyl group, acetyl or alkyl. So the maximum rate would be with the alkynyl and the least would be with the alkyl. Requirements for the chloro substrates. So again, as we have told in the Suzuki reaction, if we have a bulky phosphenes and with the electron density, they will help us to have the chloro substrates also, and basic additives that they have added for the cesium chloride, for example. So the Stiller reaction in presence of carbon monoxide, ketone formation has also been seen. So here the general reaction, we were expecting to have R1 to R2. Since it is happening in carbon monoxide, it will get inserted in that, and therefore it will give you a ketone over there. So the mechanism goes like this. So here also the first step, we have a palladium L2, which is in 0 state, and here R1X is coming, that means oxidative addition again. So R and X are in cis position. They will undergo the cis to trans this time, rearrangement. And therefore this trans has been formed. Now we have this coupling partner. So this is a kind of concerted mechanism where the bond breaking and bond making would be happening. So this S and R2 bond will break, and this new bond will be making between S and X and R2 and palladium, the way we have seen in the alkene insertion reaction. So once this goes, this will give you the X and tin bond, and ultimately we'll be having R2 and there's also one more again. So they will be having R2 and R1. Now again ligand will come into picture, and this will follow the reductive elimination, giving you +2 to 0 state, and L1. R1 is coupled with the R2. So the Stille reaction mechanism says that rate determining step is the transmetallation step 3, which is the transfer of R2 fragment from tin to palladium, as you have seen here. So this step, this third step, first step is your oxidative addition. Second step is your cis trans rearrangement. Third step is your transmetallation. Because this R2 was initially attached with the tin, now it is attached with your palladium. So this is called transmetallation, followed by the reductive elimination. So the trans step happens in a concerted way, as we have already seen, concerted way like bond breaking and bond making within a cyclic 4-membered ring. So cis disposition is necessary for the R1, R2 intermediate for the reductive elimination. And the reductive elimination step is faster than the beta elimination step over here. So this is also very important. So these are just the keynotes. So ultimately we have seen. So firstly, we saw the allylic alkylation. Second, we have seen the Heck reaction, where it is basically having the vinylic substrates in presence of bases, and it should not be having any moiety where the beta hydride elimination would happen. Second, we saw most important the Suzuki reaction, which involved the organoborane substrates, and this is having a lot of advantages. Then we saw Stille reaction, which involves tin organelles as a coupling partner, and this should also not be having any beta hydride elimination in the substrate. So these are the 4 CC coupling reactions that we have seen in the week 8. Rest others will be taken up in the next week lecture series. And now quickly we will take up the week assignment questions. So I'll be sharing up with these slides with you people, so you can have a check on it. So we have covered this so far. Hope these questions are visible to all of you. So the first question says that correct statements, bracket, there is a S also over there. So we cannot ignore the fact we need to have, it could be having one right option, or it could be having more than one right option. About palladium catalyzed CC coupling reaction is or are So the first thing that we have seen about the palladium catalyzed reaction, that they have a functional group tolerance. They can tolerate a lot of functional groups when they are there and they don't undergo any kind of further reaction. Comparatively, they are less toxic. They are less sensitive to air and moisture. Also, they are economical. Compared to rhodium, iridium, platinum. And normally the reaction temperatures have been seen to be more than or equals to 100 degrees Celsius. So these are the major points that we have seen for the palladium catalyzed CC coupling reactions. Now we'll take every point very carefully and see which ones is suitable. So the reaction is functional group tolerant, which is right, as we have said, that a number of tall groups like OH, NO2, carbon monoxide, CN, etc., they would be functional group tolerance. They are highly toxic in nature, as we have said, in comparison to other noble metals, they are not. So this is the wrong option. The reaction is not very sensitive to air and moisture, which is right. And the reaction requires temperatures below minus 100 degrees, which is not at all true. So one option A and C are the right options. Correct. Now we will see the second question. The steps 1 to 3 of the following reactions respectively are. So the mechanism has been given in a just one line reaction, and you need to find out what is step 1, what is step 2, and what is step 3. As we have gone through all the 4 CC coupling reactions, we have seen more or less they are same, but with a slight difference. We need to be very careful. So this is a general CC coupling mechanism. So you don't have to worry about what is happening in Suzuki and what is happening in that particular thing. So Rx is added up to the palladium 0. It is going to palladium 2. Then nucleophile is attacking. It is going R nucleophile. And then it is releasing the R nucleophile and palladium 0. So what happens here? Firstly, we know that palladium 0 is coming from where? If we are having an acetate over there, we are giving 2 times L, which is PPH3, suppose, and it will go to L2. This is 0 in presence of base. Then when we are adding the Rx, so the first step goes as oxidative addition. Why oxidative addition? Because it is going from its 0 to +2 state, and also it is undergoing addition of R and X to palladium. So this will be forming like R and X. Then L2 will write over here. Then we have nucleophile and M. This could be anything. And this step we call it as transmetallation, where M and X will go as MX and nucleophile will go in its position. And ultimately, the last step, since it is in +2, it has to regenerate the catalyst path. It will be going as palladium L to again 0, because the electrons would be donated by the R and nucleophile, which will couple together to give you R nucleophile. So this step is the reductive elimination. So why reductive elimination? Firstly, palladium +2 is taking up 2 electrons, giving up palladium 0. The 1 electron is coming from R negative and other from the nucleophile, and ultimately the elimination of your product. So this is what we are having the whole mechanism, and now we have to see. So first step was the oxidative addition. So all of them are oxidative addition. The second step is the transmetallation. Now see, The second step is reductive transmethylation, nucleophilic addition, electrophilic. Only this option is correct. And the third step is the reductive elimination. So B option is correct. And these are not at all the options because electrophilic substitution, nucleophilic substitutions are not happening. But in A and B option, the transmethylation has been given as a last option. So you need to be very careful, even if you know that how the things are going to look like. Doesn't mean that you can shuffle it. It has to be a proper, like step one is oxidative addition, then followed by reductive elimination, then followed by transmethylation, and then reductive elimination. So this mechanism is clear. Now we have third reaction. The reactions that are catalyzed by palladium is or are. So hydroformylation reaction is involving actually a rhodium catalyst leading to CHO. So Sonogashira reaction that we have not read so far, but it is also a CC coupling reaction, which involves the palladium. Heck reaction, we have already seen CC coupling, which involves palladium. Sharpless epoxidation reaction, it actually occurs in presence of titanium-based catalyst, which will form epoxy alcohol. So we are not going into that particular thing. So these only are the CC coupling reactions which will be catalyzed by the palladium. So now the fourth question says the step A of the following catalytic cycle is. So step A is almost similar in all the CC coupling reactions. Without the step A, it is not going to move further. As you have seen, the palladium L4 will lose the 2L, and if it is this case, palladium PPH3 whole 4, then it will lose two PPH3 molecules, will give you the palladium in 0 state. Now this is the moiety R and X. This is forming and they are asking A as what? So it is nothing but your oxidative addition because X also has been added and the R also has been added to the palladium, converting its oxidation state from 0 to +2. If we'll see the next steps, as we have seen, this is nothing but the allylic alkylation. So this is a sigma bonding. Now the next step is sigma by rearrangement, where the allylic sigma eta 1 goes to the eta 3, eta 1 to eta 3, followed by the loss of X, which has come outside. Now the attack of nucleophile insertion, and therefore it is giving neutrophil attack is happening. And ultimately with the reductive elimination, it will give you the product. So it's only the oxidative addition at the first step. It's not that it is not happening, that sigma pi rearrangement is also happening, flip attack is also happening. But the first step here is, that has been asked, so we need to be very careful. Now the fifth question says the product of the following reaction is. So as you remember, this is also a type of Heck reaction. Firstly, the catalyst is palladium, and these are the vinylic substrates, reagents that we are using. So this particular moiety is R, and this particular moiety is R dash or something like that. So it will be having a coupling reaction in presence of the base. So as you know that the major product would always be a trans product, even if whatever the conditions we are taking. So as you can know that this format will not change, but there would be a bonding between the two. Br has to go because it will be taken up. And as you can see, this option, which is having Br, is not going to work. And here, the CO2 moiety cannot go to that particular direction. So the bonding is going to happen between these cinders. So this option is correct. Sixth is the major product. Again, the vinylic kind of reaction. We have PHX and we have another moiety PH and this vinylic position. Now they have given the triplet and the solvent is THF. Anyway, for the polar solvent, less polar solvent compared to the water and something, the trans would be the major product. Anyway, it is major product, but for example, in this particular case, it will be 92%. So that we have to see whether the cis is being found or this having X, which is not right, and pH at this particular position, that means it is cis or something, and this one is trans. This one is cis and this one is trans, so this is the right option for us. So only the basic thing that we need to see in Heck reactions. X negative moiety and the solvent plays a lot of important role. If it is non-polar or less polar, trans is the more than 80%. And if it is polar, comparable ratio. Cis and trans, but trans is the major problem. This we need to remember. Now the seventh question says that again the step A they are asking. That's a very straightforward reaction. Now this is an example of Suzuki coupling. Earlier was the Heck coupling. So here you have seen we have started with palladium 4, which could be PD, PPH3, 1/4, or we are taking the salt, which is in +2, this is in +0, with the ligand, and it will give you a palladium in 0 state. Now when Rx has to come, it is getting added. So A step becomes again the oxidative addition. I'm just repeating that it is going from 0 to palladium +2, and also it is having the addition of R and X moiety. Now, in the presence of the this side reaction, the organoborane, it is in presence of base, it will get formed into the anionic form, and therefore this charge transfer, that carbanion transfer becomes even more facile, and it will take up this X. Ultimately, we'll be having R and R dash. This would be a trans cis. This is also called transmethylation step. And here cis trans rearrangement. And ultimately, with the reductive elimination, we are having our product out. So the first step they have asked, so it is not, they have involved all the steps, but you need to be sure that it is an oxidative addition reaction. Now the 8th question says the following reaction is example of which CC coupling. So there you have to again be very careful what kind of reagents you are using. The catalyst would be more or less same and basis also. But one thing that you can highlight here, this is an organoborane coupling partner. So which is for the Suzuki reactions. You don't have to even look at the product, just see this reagent and the tick mark. For example, in Stille reaction, we know that this kind of SNR3 would be there. And in Heck, there would be phenylic moieties mostly. So with absence of this tin or boron, sonoxira, we will see in later point of time. So this is very important. Now the structure of retinol, vitamin A, this is also from a Suzuki coupling application, where if you remember that it was having iodine, and other side also it was having so something related to either OO or something like that was there. So when we are having this kind of moiety, they will couple together in presence of the palladium channels, which is called the Suzuki coupling, and therefore the C option is the right one. Where okay. Now the last question of this week assignment is the following reaction is an example of. So here, if you see, the product is not a CC coupling. It's not a CC coupling. It's a bond between this C and boron. So that is why it is hydroboration. It is neither Suzuki nor Heck. Just looking at this particular thing, if you will mark it as Suzuki, that would be a wrong because you have to see the product also. Haloboration, if it would be having a halogen loss, then it would be at haloboration. But right now it is a hydroboration because here the bond is between the C and boron. So here this H is going to attack on this carbon and this becomes a alkene and therefore backs attack on the boron. So this is nothing but your hydroboration. So yes, this is all about the week 8 assignment problems. So I hope I have cleared, made a right explanation for all the questions. Uh, if you find any problem in understanding any other questions and solutions, you can just unmute yourself and ask me a question. So since there is no further question, so I will end up this meeting and we will meet next Tuesday from 6 to 8. If you guys have any question, you can just drop a mail or can ask me questions in the next week. Thank you.